Today we've got a full session, not so much on the decision-making aspect, but more on the data aspect and the data governance aspect, which is the other important sort of focus of this lecture series. Big datafication and the governance of knowledge production is our topic today. And for that, it's my great pleasure to welcome two colleagues from our research platform, Governance of Digital Practices, Paul Dunshirn, who is affiliated also with the Department of Political Science, and Rasmus Waderman, who is also affiliated with the Department of Science and Technology Studies. Briefly, who are Paul and Rasmus? Paul has a background in anthropology and political science from Vienna, also a social sciences master's from Amsterdam, and his current research explores the governance or the governing of common resources, for instance, or mainly, I think, maritime biodiversity through digital platforms and the various sort of policy and political questions involved in that. Is part of the Maripol data research group within our department. And I'm sorry, that's my phone. And Rasmus has a background in sociology and science and technology studies from Norway. And the focus of his current research is on the digital transformations of work, specifically academic work, perhaps, or more broadly, work in knowledge-intensive sectors. The reading for today is an article by Sabina Leonelli, published in the Harvard Data Science Review. Data governance is key to interpretation, reconceptualizing data in data science. That is already online. So Rasmus and Paul will jointly deliver this lecture today. As always, our format is we'll have a talk of an hour or so, and that will be followed by Q&A, and you'll have a chance to raise questions later on through the chat or through the mic. Okay, gentlemen, it's a pleasure to have you here, and the floor is yours.
Thank you very much, Lucas, for this kind introduction. It's also a pleasure from our side to be here tonight and to present to you the topic that we came up with for this part of the lecture series. As Lucas said, it's big datafication and the governance of knowledge production. And we will jump right in. Sorry. To give you an idea of what we want to talk about tonight, we'll first give you a brief introduction of key terms that we're working with, including big data, algorithms, and science, and talk about how they relate to each other and how they relate to governance challenges. We will then have a part where we dive deeper into the historical developments that constitute this process that we label big datafication of sciences. And then my colleague Rasmus will talk about critical data studies and identify some of the challenges of the big datafication of sciences that emerge from these historical developments. And finally, we will talk about governance models, governance frameworks to address these challenges. Okay, so, and similarly to what Lucas already said in the introduction, so far in this lecture series, the focus was mostly on decision support, right? Or decision making in the form of algorithms. And there is this definition by Latzer and Jus from the very first session of this lecture series about algorithmic selection systems, understood as input, throughput, output systems. And so the algorithms are the throughput element of this system, right? And today we are going to focus more on the input, so on the data that feeds into the systems. And we're going to talk about this in the context of science. And in this context, you can observe an increased use of algorithms and big data in various scientific disciplines over the past decades. And this has started in disciplines such as physics, mathematics, geography, astronomy, life sciences, But more recently, it has also expanded to other scientific fields, including social sciences and humanities. And it's always a little bit difficult to define big data. Indeed, there are quite controversial discussions about how to confine or how to delineate this phenomenon. But for the purpose of our lecture, we are going to work with a loose definition of big data, which essentially, in our case, means practices and discourses of large-scale data creation, sharing, and analysis. This is our working definition, and I give you illustrate to you very briefly what we mean by that. So consider the case of COVID-19. We've become quite used to having a lot of numbers around us about infection numbers, transmissions, origins of transmissions, and so on. And we, I guess, sort of taking it for granted by now that we have all this data and we hear about this data in the news and so on. What is important for the context of our lecture is to understand that it's not obvious that we have all this data, right? Indeed, this data is, the availability of this data is the outcome of large-scale efforts by scientists, by policymakers, and by technicians to actually create this data in the first place, but then also to share this data and make it globally available, and also to analyze this data to understand the nature of this virus and its spread. And what we also wanted, so this was the first part, right? The sort of practices and practices that go into the big datafication of science, right? This large-scale data sharing, large-scale data creation, large-scale data analysis. But we also want to talk about the challenges that emerge from this big datafication process, which include a certain risk to overestimate the capacities that big data have, right? There's often this assumption that big data captures everything that is happening because it is big, it is endless in scope to some extent. So, and this kind of understanding of big data neglects a lot of issues about the completeness of every data set, about the quality of data and so on. So there's an epistemic issue in this sense. And we can see this in the case of Omicron, where it was sort of wrongly termed the South African variant, even though later on we found out that this variant existed in Europe even before it was detected in South Africa. But the data told us at first that it was in South Africa where it emerged, right? Then another issue we are going to talk about is issues around equitability, or as we provocatively phrase it here, a science only for the West. And this relates to the question of who contributes and who benefits from the big datafication of science. So we can also see in the case of the distribution of COVID vaccines, which is highly unequally distributed, particularly when it comes to African countries. But this is just to give you an idea of what we want to talk about, and now we dive further. We take a closer look at the historical developments that constitute these transformations in science. And Sabina Leonelli talks about this as well in the assigned reading for tonight. And she makes this point that back in the 17th century, data were seen as fundamentally private objects that were owned by the scientists that created them, and their value in terms of the analytical insights that you can gain from them were quite delimited to the spaces of inquiry that these scientists had in mind when they first created this data. And she goes on to argue that since then, there is a shift in perception of what data is and how we can use it. And now there's an understanding that data is powerful yet unpredictable objects, and their value is not fixed, and may increase the more data are shared. We can see this also in the case of the COVID-19 data, right? That if only, I don't know, if only Austria would sequence these genetic materials and would not know about where these infections are coming from, and would not know about health consequences of this virus previously to entering Austria, then this would be quite problematic for our understanding of the virus. So this is what we mean by the more shared, the more data we have, the more it's shared, the more value there is, in a sense. So that's quite a different understanding of science and of data. And now we look a little bit closer at how has this shift come about, shift in understanding. So there's this term big science, which emerged in the 20th century, which has a lot of parallels to the big datafication of science. And what big science means is it's a type of science that is incredibly costly, that involves hundreds or thousands of investigators. It has quite an extensive management structure and is supported by a very large scale, has very large scale public support, but also public scrutiny. Few important examples of big science are the Human Genome Project, but also CERN, or in physics, or the Very Large Array, which is an astronomy research project. And there are quite a lot of parallels, as I said, between the emergence of big data in science and these big science projects. And we'll look at the Human Genome Project as an example of this, how this came about. So the Human Genome Project lasted from 1990 till 2003. And it was a publicly funded research effort to generate the first genomic reference sequence for Homo sapiens. And it was not only publicly funded, but it was globally, it was funded by an alliance of states. It was a sort of a global research project that consisted of a network of laboratories were distributed around the globe. And they engaged in this practice, and it's these daily practices of data sharing, data analysis within this network of laboratories. And it's widely regarded as a very crucial project for the development of molecular biology and for the development of key genomics technologies, including technologies that go into innovations like gene-based vaccines and so on. This has, like I said before, as a big science project, it has gotten a lot of public attention, including from President Clinton and Minister Tony Blair, which have talked about how important this project is for our understanding of the causes of human disease, and that it's going to bring about a new generation of effective treatments in the prevention of diseases and cures. They also talk about how important it is that data is being shared, data of these human genome sequences, that they are shared and that they are released into the public domain. And they also addressed the important role of intellectual property protection in the form of patents to sort of stimulate innovation after the publication of this data. And this is very interesting. Yeah, I will respond to questions after we are done in the final half an hour, if it's okay. I think that's the plan for this lecture. Okay, but so this data sharing that is being praised by Clinton and Blair this is what we want to focus on here, right? Why did they start sharing the data? Why has it become so important? And indeed, these data sharing practices have been formulated in the so-called Bermuda data sharing principles, which were published by the leading scientists of the Human Genome Project. And they prescribe these practices of sharing sequences with the public domain. And it's actually, there's a song by Francis Collins, who was one of the leading scientists of the project, where he's singing, "They worked without resting and gave it away," which it's quite telling for, they have such a huge effort to produce all of this incredibly large amount of data. And then they basically published it for everyone to see it, right? And this is not logical that scientists would just share what they have worked on for so long. And there are different approaches to explaining why this idea of data sharing came about in that context. One explanation is a pragmatic one about these data sharing practices having had a long-standing tradition in molecular biology as important to the research itself, right? That you would collect a lot of samples from very different contexts and would compare across contexts in order to draw conclusions. But at the same time, it also relates to the sort of organizational requirements for running such a large-scale research project on a global scale, in a sense. Which relates to issues around project coordination and quality control, these scientists came up with data sharing as a technique to deal with issues of quality control, for instance, that there is some transparency to keep the standards high across the different laboratories. There's also this idea that openness is a value in itself. So something more normative that scientists commit themselves to voluntarily. And this can be partially be traced back to the involvement of computer scientists in the Human Genome Project, who were inspired by or who were part of the free and open source software movement. But more generally, there's this idea of a knowledge commons. So that these genetic sequences should not be considered as private goods that are owned by clearly defined scientific institutions or individuals, but it should be a public good that everyone can contribute to and profit from, you know. And finally, there's also an economic line of argumentation, which is a little bit contradictory, because the sharing of data had both the effect to encourage patenting. As I said before, this is what Clinton and Blair address, that if you have access to this data and it's free, this is supposed to encourage follow-up innovation using this data, because the access is very, very easily established, right? if it's freely available. So innovation to develop vaccines or other products. But at the same time, there was also an idea to prevent certain types of patenting that would create obstacles for science. So by publishing data and by publishing knowledge, it prevents certain patents from being issued, because they wouldn't constitute inventions anymore, because the knowledge was already patented. It was already published beforehand, right? So everything that happens afterwards cannot be considered as a new invention anymore, thus it cannot be patented. Okay, finally, to close off this section on the history of science, we're looking at the more recent developments, or what has happened since the Human Genome Project stopped. So in the context of genomic research, there was a proliferation of open databases, essentially. So And this is most specifically can be seen in the case of the International Nucleotide Sequence Database collaboration, which is a huge international collaboration between the three biggest genetic sequence databases. So the American database, the Japanese database, and the European database. And they all share data with each other on a daily basis. And they don't just share, they mirror it. So essentially they have the same content in all three databases. And this is, what you can see there is this trend towards more and more data amassment, and combined with that trend towards machine readability, which becomes important if you have this basically endless amount of data. Human beings cannot analyze that anymore. So that's where the door to algorithms, machine readability opens up. You also have you also have the development of technology sinking in costs, which is I guess a long-standing development, but has become even more prevalent recently. Also in the field of genomics, where genomic sequencing technology is so much cheaper than it used to be at the times when the Human Genome Project started. Also, the cost of just owning a computer is much less than it used to be. And all of this contributes to this trend towards more and more data. And you have the expansion of open data movements way beyond the life sciences and these other sort of big science projects where this idea came from originally. Now we're going to move on to my colleague Rasmus about critical data studies and some of the challenges that emerge from this process of big datafication.
You're absolutely right, Paul. Thank you so much. So the main idea that I wanted you to take from Paul's first part here is that there's more and more data in science. And so as part of science became more saturated in data, as we call it, it also became more data intensive, as Paul already mentioned. And what we mean by this is that back in the day, researchers, they had to rely more on their creativity, interpretation, and analytical skills to squeeze knowledge out of the little data that they had. But now, as scientists are more swimming in data, more of the knowledge produced stems from the data itself. At least that's what some people will have you believe, but I also will warn you to accept this premise too readily. And around the beginning of the last decade, several social scientists started to notice that this change was happening and that something is happening with data and how we relate to it. And they realized that, in short, that over time, the importance of data has grown, becoming central to how knowledge is produced, business conducted, and governance enacted, as Kitchen and L'Oreal put it. And this big datafication, it happened faster than our ability to understand what it would mean for our society. So answers to old challenges, they no longer applied necessarily. So researchers organized themselves around establishing new questions. And the one we'll be focusing on in this lecture stems from Boyd and Crawford's Critical Questions for Big Data from 2012, where they ask whether large quantities of data will transform science or narrow the palette of research options and alter what research means. And you might think that's, Paul, would you change, please? Thank you. And you might think that it's a bit overly dramatic to worry so much about large quantities of data. Because after all, if we are to believe the people who claim to know the most about the topic, big data will solve your email problem. It will solve the dilemma between choosing a taxi or an Uber. It will revolutionize sports. It's revolutionizing manufacturing and agriculture and so forth. But the most provoking and most cited praise of big data came from Wired magazine's editor, Chris Anderson, claiming that big data would usher forth the end of theory. And in this article, he posits that with enough data, the numbers speak for themselves. And this made a lot of people very upset. And since that, other scholars have looked into how different actors see, understand, and imagine data. So some of the most recurring beliefs are that data is raw, which means unadulterated, that it's an objective representation of reality, that it's inherently valuable through its potential to create knowledge, and that it is universal. And these beliefs together, they suggest that data is a very powerful thing. And this power can be very seductive. So you can imagine what happens. If people believe that data has this power, they will do their best to reap its benefits. And the Human Genome Project, as Paul mentioned, is itself based on this belief that with enough data about the human genome, we will be able to revolutionize the diagnosis, prevention, and treatment of most, if not all, human diseases, as Bill Clinton put it. And this belief directed $3 billion into what was back then seen as little more than a scientific niche. So this belief, dubbed the data imaginary in science and technology studies literature, it has immense power to change and shape the decisions of people and society in particular ways, which we will look into now. So that question is, why do we worry about this? Because as long as data delivers on its promises, we should be good. But the problem is, of course, that it doesn't always do that. Because what happened after the Human Genome Project? In 2010, a decade later, genetic map yields few new cures. In 2020, we've sequenced the human genome, so why haven't we cured more diseases? So the data imaginary failed to deliver for the Human Genome Project, at least partially, but it didn't only cost money. It has also been widely criticized for reproducing global inequality by largely forgetting about non-European genomes and for not reflecting the needs of low middle-income countries. But despite the Human Genome Project's problems, the belief in big data has never been stronger. And that's why the Critical Data Studies tasks itself with scrutinizing how this data imaginary is expressed in the world and anticipate its consequences, in case it's bad. And spoiler alert, as you might have gathered from previous lectures, sometimes it is. And to show you this, I'll go through two of the main critiques from the field of critical data studies. The first critique, it centers around the so-called epistemological shift in science. And this is what Boyd and Crawford refer to when they talk about big data narrowing the palette of research options and altering what research means. So this is very simplified, so don't quote me on this. The production of knowledge is based on two elements. It's data and the interpretation of it. You look into a microscope and you interpret what you see, or you observe a tribal community in the Amazon forest and you interpret what you experienced, or you might read a bunch of documents and interpret what they mean, and so forth. So for us to trust the knowledge produced from this process, we have to trust both the data and the interpretation or the interpreter. It fails if I trust that the cells in the microscope is a true representation of a bacteria, but I don't trust the person telling me that it means I have to wash my hands after I go to the bathroom. Alternatively, even though I trust the anthropologists, I don't trust that the tribal community in the Amazon forest acts like that when he's not around. So in reality, this is of course a way more complex process, but for the purpose of this lecture, this will have to do, and I'll be happy to discuss this later if you're interested, but let's accept for now that knowledge is data plus interpretation. Okay, so generally speaking, this arrangement has been working pretty well for hundreds of years, but the ways we trust have also changed over time. So rationalist philosophers might argue that all you need is one certainty or data point, if you will, which is called an axiom. And the interpretation or rational logic can produce knowledge from that. So I think, that's the data sort of, therefore I am, that's the interpretation. So this method has its limits. There's only so much knowledge you can produce from only thinking, and there's good reason not to trust all of it either. And that's why contemporary science usually is more balanced between data and interpretation, of course, as we know it today. But we've gotten some issues with contemporary methods as well. There are people who don't trust science, this type of science. I'm not talking about climate deniers, vaccine skeptics, and flat earthers, even though they are a very real problem and exist, of course, because even among more reasonable people, like 90% of the scientific community, there's a panic. Our one method for checking if knowledge is any good is failing. We're in the so-called reproducibility crisis. The problem is that we see bias, subjectivity, and inconsistency everywhere. We don't trust the interpretation or the scientists. And therefore, the suggested solution is we lean more on data because according to the data imaginary, that's what we can trust. But although more data can be good for reproducibility of knowledge production, it also has a less fortunate side effect because Just like philosophical rationalism is limited in its ability to produce varied knowledge, so is dataism. So if you only use the numbers and data to see the world, we might end up believing that US cheese consumption leads to more people dying by becoming tangled in their bed sheets, and thereby ask people to eat less cheese in order to curb this tragic development. And rational actors would never make the mistake to blindly trust these numbers when other observations were telling them it was wrong, especially in situations of great importance, right? This is, of course, a rhetorical question, and the answer is, of course, yes, they would. Historical example where the belief in data had grave consequences was during the Vietnam War. When the conflict was raging at its worst and public outcry in the American population and among military personnel was at its loudest, the Secretary of Defense in the US, Robert McNamara, insisted they were wrong, because according to the numbers of fatalities and captured armaments and so forth, they were winning. As it says in the quote, McNamara sought truth, and that truth could be found in data. The consequences, of course, is, as you might know, countless lives lost and one of the most humiliating defeats in US history. And today we can find similar tendencies in the way we understand and act upon COVID, as Paul already mentioned, because we see the pandemic through numbers, whether it's numbers of infected people, it's percentage of free hospital beds, or maybe even numbers of antibodies in your bloodstream. So these numbers have been very helpful, but as Paul mentioned, sometimes the numbers can make it seem like South Africa is a hotbed for COVID mutations, when in reality, they're just the ones that are first identify virus that most likely developed somewhere else. And the question is this what we get from a science of only numbers? So the second shift of big datafication is the shift in valuation. Basically that we as a society, we appreciate and care more about data than we care about interpretation of data. Because what are we paying for when we're paying for science? I'm talking about money. After the world wars, at least in the States, the idea formulated by this guy, Vannevar Bush, was that science could figure that out on its own. We should fund science because it makes us better, and scientists themselves should be allowed to decide what would produce the most good themselves. Give us money and leave us alone, sort of what he's saying. And if it ever was like this, it isn't anymore. Today, you would typically get your funding from a public or private institution that have their own interests at heart. More or less, regardless of the topic, funders, but also journals, increasingly want scientists to publish openly. And this applies not only to articles and books, but also to data. The general idea is that instead of these scientists sitting on all their data themselves, they should share it so that other scientists can use them too, and then produce more knowledge and then more value. And because all this data is openly available to everyone, it's also good for everyone. Win-win, or so it seems. The first problem is that the analysis of big data demands both data scientists and advanced computing capacity in addition to just the data. So without the competency and computing, big data is just numbers and spreadsheets. It's noise without a pattern, so to speak. So you need resources to make the data valuable. And there's unfortunately no number for how expensive building a functioning data infrastructure costs, but in the European Union alone, the cost back in 2016 was estimated to be in the billions. And these are billions that the EU are currently spending. But not everyone has that amount of money or can afford to prioritize digital infrastructure when other issues are more pressing. But you can say, what if we invest in capacity building and technology transfer in these countries? Wouldn't that help? Well, not necessarily. Because it's not only in low middle income countries, there's a demand for data scientists. Europe is struggling to meet its needs and is putting tons of money into fixing the problem too. And since they're in such high demand, the top talent is likely to get poached by the ones who can offer the most, either in industry or in research, typically Google or Amazon and so forth. This effectively creates a brain drain of the needed expertise. Paul, if you would. So even if you're able to train the needed experts, you might not be able to keep them without the resources for incentivizing their stay. And this effectively means that in some regions of the world, the keys to unlocking the value of big data, they're simply out of reach. So the second problem is that even if low middle income countries built infrastructure needed to make use of big data, they wouldn't necessarily be able to reap the benefits from it either. So the problem sort of lies in the data itself, because researchers aren't entirely free to generate the data they are most interested in themselves. As Staunton et al. Put it, the research agenda is not set by local research needs, but rather by the funders of research. So researchers who want to get funding have to turn towards those who can offer it, and that is typically bigger funding bodies in the West. As a result, low middle income countries end up producing data that is more helpful for other regions of the world. So one example from genomic research comes from the leader of the African Society of Human Genetics, Ambroshi Wankam, who stated that despite recent progress and investments, too much of the genomic research done in Africa has been driven by European and American investigators. Why is this a problem? Their priorities could be detached from what people on the continent need and want. What good is identifying variants for breast cancer or cardiovascular disease in people who can't get mammograms or checks for high blood pressure, and who probably won't have access to medical treatments? So despite a growing body of data that's openly available for everyone, it's mainly countries that already have a lot from the beginning that benefit from open data. So the question is a data-intensive science then a science for only the West? So now we say enough with the questions and critiques for a little while, and we look more at how science is reacting to this change. In other words, how they are governing the big datafication of science. So small recap, science is undergoing a big datafication, and there's a reason to be concerned, or several reasons to be concerned. And as Sabina Leonella put it in the reading for today, concerns around interpreting data and assessing their quality can be tackled by cultivating governance strategies around how data are collected, managed, and processed. And that's why we're going to show you two empirical examples of governance strategies from our own research and how they deal with these concerns. Yeah, but first, before that, even a brief conceptualization of governance, because when we're talking about governance, in this case, we're not just talking about the narrow understanding that, governance is purely laws and rules. We understand governance as a more complex process of interactions that produce particular relationships, and most importantly in this context, power relationships. And we've already been through some models of governance in this sense. The scientist that Paul mentioned at the beginning in Leonella's quote, who saw data as private, giving him the absolute power over his own data. And we've been talking about open science, where all data is supposed to be shared openly and freely, in a sense revoking the scientists or data producers' power over their own data. But the cases we will talk about, they exist somewhere in between these two strategies of governance. And we'll start off with the FAIR principles. The FAIR principles were conceived in 2014 at a small conference in Leiden, Holland. The people behind this idea, they recognized that life sciences were producing ever more data, but they were unable to make sufficient use of the data. It was wasted, and they wanted an end to this waste. And according to their beliefs, sharing data openly was a step in the right direction, but it wasn't enough. Data had to be made FAIR, which stands for findable, accessible, interoperable, and reusable. And in their eyes, it was not enough just to put your data out there like in open science, but it needed to be given more attention so that others could use it, actually reuse data. And this meant uploading the data to particular databases and producing detailed metadata and making sure that the format of the data was according to certain standards. And the end goal of this idea is to create the so-called Internet of Fair Data and Services, where data can be uploaded, used, and analyzed by humans, but most importantly, as Paul already mentioned, machines. And this is supposed to happen regardless of discipline or geographical location. And this is also supposed to enable the full extraction of value from data, so to produce knowledge and innovation in novel ways at a larger scale and at a lower cost than in current regimes of science. And needless to say, this is easier said than done. So further, I'll present some of the challenges this initiative has met and how it aimed to solve them and potential issues that actually might create later on. The first barrier is that data is not valued enough in contemporary science governance. And after all I've said about data increasing in value over the years, this might not make much sense, but you should just hear me out. Because in today's regime of rewarding science, there's two main things that are seen as valuable. There's, of course, a bunch of other stuff depending on different factors, but in the end, it boils down to these two: funding and publications. And the publications are preferably in high impact journals. So let's start with publications. Because why do researchers want to publish their stuff all of the time? For one, you'd like to share the knowledge you've spent so much time to produce. Second, your funding might require it. And third, the amount of publications in high impact journals is generally how we define anyone's worth in academia. So whether you want to get hired at a prestigious university like Harvard, or you want to negotiate a higher salary in your current position, if you don't publish, forget it. And this is often called the publish or perish paradigm. You might have heard of it. So, understandably, researchers become obsessed with publishing. They publish articles and books and editorials, and they get rewarded for it, but they don't get rewarded for publishing their data, generally speaking. So nobody really recognizes anyone's effort in producing and sharing data, and that's why most people generally don't unless they have to, and this is most people. So the system where publishing is the main source of academic clout, it has been criticized for many years, most notably through the DORA Declaration from 2012 from San Francisco and the Leiden Manifesto from 2015. And both of them want to change how we value scientific work, or you can put it this way, how we govern science. And this process of changing the way we govern science is happening really, really slow, and science is still perceived to be stuck in its old ways. But over time, maybe we'll see scientific institutions following the DORA Declaration and recognizing additional products such as data sets, as they put it. But the question then is, will data production be seen as more attractive than knowledge production? What happens then? But let's get back to funding. Why do researchers care so much about funding? Well, funding is needed to have a salary, to get research assistance, and basically, anything you'd want in academia. It's pretty self-explanatory in some way. Money is nice to have. And if you want money, you can get it through applying for funds or grants, which usually have some predefined criteria like solve cancer, do it within 3 years, and using no more than 1 million euros doing it. Maybe it specifies that you have to collaborate with researchers from other countries and disseminate your research underways on a blog or something, and also make your data open. But generally speaking, that's the basics of it. So the funders haven't usually been asking researchers to make their data fair, which is where the issue arises, because that would cost more money, say 1,050,000 euros instead. And the funders haven't really seen that as a valuable investment as of yet. And the result is, of course, that no one pays for it, only those who really care about it and are willing to do it. And those people are, in a clear minority, actually. In fact, only 28% of researchers asked in the State of Open Data survey even knew that the FAIR principles existed and what they were. And that's why people behind FAIR have been working so hard to convince funding bodies that these 50,000 euros, they're not wasted, they're actually, a good investment. The question shouldn't be, what is the cost of having fair data? Rather, it should be, what is the cost of not having fair data, as it is put in this PricewaterhouseCoopers report for the European Commission. And for those who are interested, the estimated price in the European Union alone is 10.2 billion. Although the authors are confident this is much higher than that. So this move generally seems to have done the trick. And now all research projects funded by the European Union's Horizon Europe funding program is obliged to make their data fair. But as of yet, they seem to be operating with a pretty soft understanding of what fair means. And we can assume that a lot of people are getting away with pretty standard data management. But if this becomes more strictly enforced at some point, we could be asking, what happens with those who don't have the facilities and knowledge to make data fair? Are they left with fewer options for funding than those who have the competency in-house already? So the second challenge is one of legitimacy. The European Union is knees deep in FAIR already, as you might have understood, and the United States, they are dipping their toes too. But who do you think have been hesitating to get in on this new venture? You guessed it, it's the low middle income countries. Because FAIR is a very data-centric initiative. It's all about making more data available in a better way. But as you might have understood from the previous slides, more and better data isn't necessarily that interesting for low middle income countries. Why should they be interested in contributing data to the Internet of Fair data and services? What do they get in return? You might think this is a little bit petty, but previous experiences, they give them a pretty good reason to think twice about this. Historically, within the open data framework, low and middle income countries have felt that they've been exploited in what can be seen as a neo-colonial relationship between the West and the rest. But simplified, the relationship has worked like this. Low middle income countries produce data, typically genomes, on life forms that exist in the local environment. Then someone from the West takes that data, analyzes it, gets some publications, maybe even without acknowledging the work of low middle income scientists, and then maybe produce a patent from it so they can make money by selling drugs back to the low middle income countries, as it happened during the Ebola outbreaks. And in a way, this is also what is happening now with COVID. And people are understandably not having it. Researchers want to retain the control over their data, not just give it away to someone with no regard for them. So why would they want to take part in FAIR, which is a concept designed in large by Dutch guys? So to give a possible answer to that, we point to the fact that although they're often seen as versions of the same, FAIR and open, they're not the same. Part of the problem, it stems from that open community seeing FAIR as sort of like a supplement and including it in their promotions of themselves. The FAIR community has therefore been working hard and continuously in publications and conferences to create a safe distance from open, saying we are not the same. FAIR is in fact very critical of open and its disregard for control over data. FAIR data is meant to be accessible, not openly available. And there's a thin line there where the FAIR principles are designed to allow data producers to set their own terms for use and access. For example, you could say your data is available to anyone who would want to use it, but you claim the right to co-authorship in case someone goes into publication, or you can restrict the use for commercial gain. In theory, this works out pretty well, but in practice, it might be hard to enforce. Just like I'm using this picture from Star Trek, which is, technically and legally speaking under intellectual property regulation. And to make it worse, we don't really have a good legal framework for data ownership and sharing, even in Europe. So there's still a way to go. But, on the more optimistic side, experience from the COVID pandemic has shown us that researchers from low middle income countries, they're more inclined to share their data under stricter governance than just open, as with the GISAID data repository for COVID data. Many researchers who work with GISAID say that its terms of access are a benefit because they encourage hesitant researchers to share data online speedily without fear that others will use results without credit. The reason so many labs have provided SARS-CoV-2 genomes to GISAID is precisely because of the data access agreement that restricts public resharing. If FAIR can convince low middle income countries it will grant the same protection, it might have a chance. The question then is, will FAIR be able to offer an equal distribution of value for all participants?
Thank you, Rasmus. To close off our presentation, so I will talk about a second sort of governance framework next to the fair data sharing principles. We want to briefly tell you about so-called access and benefit sharing mechanisms, which are a framework that, similarly to what Rasmus just said, should sort of like address this question about who gets the benefits from big data, right? And it's a little bit different than the fair data sharing principles because it is actually a more formal policy that is pursued by states in international treaties. But let's first start with these bottom-up science governance initiatives that Rasmus talked about, like the fair data sharing principles, originally at least, which regulates science already, as Rasmus described, right? Other examples are the Bermuda data sharing principles that I already talked about previously. Also nowadays, journals and funding agencies often require scientists to donate their data to open databases in order for them to get their publications accepted. But what is quite interesting in these sort of bottom-up science governance governance frameworks is that they always have this tension to national science policies, right? So they're often some contradictory elements about which data can be shared, which data should be shared. Also regarding privacy concerns and so on. But what we can see in all of these sort of bottom-up governance initiatives is that there is a focus on questions about access, which is also prevalent in the idea of open access databases, or also to some extent in the fair data sharing principles. But these questions about benefits from big data are often sort of like neglected in these bottom-up initiatives. And this is where, interestingly, in international politics, so at the level of international politics is where this issue has gotten addressed, at least in the context of genomic research, particularly in the Nagoya Protocol to the Convention of Biological Diversity. In this visualization, you see the member states of this treaty. And this is the Convention of Biodiversity is a treaty to conserve and use biodiversity sustainably and fairly. And I guess the interesting question is how to ensure that this biodiversity is being used fairly, right? This is the key question here. In order to start assessing this, they have introduced this definition of genetic resources, which are understood as genetic materials of potential scientific or commercial value. And importantly, this excludes human DNA sequences. So something like what the Human Genome Project did does not fall under this convention, but it includes virus DNA, right? So it does include something like COVID-19, the data on COVID-19, because this is not per se human DNA, but it's virus DNA. It's natural. It's a natural resource in a sense. And how does this convention address the question of benefit sharing? And interestingly, it has this. It combines both of these questions of access and benefit. It is sort of a balancing act between the two. And what it does is it obliges all actors that are involved in the sequencing of genetic materials to enter these bilateral agreements between the providers and the users of these genetic sequences. So these are essentially agreements between communities, including indigenous communities that might have sort of indigenous knowledges about the health effects of certain plants or so on. And if researchers from the West now want to visit these communities and do research on these using these traditional knowledges, they would have to enter these agreements with the communities, where it is obligatory to explain how does the community, so how do the providers of the knowledge benefit from this research that is being done. So this is quite an innovative governance institution, if you may. And it also involves the necessity to get prior informed consent from the country of origin. So it has a strong sort of national sovereignty dimension to it as well, where countries have the option to just decline certain research from taking place if they feel like there's not enough benefit that flows back into the country of origin. Now, there is a question about how these benefits look like, of course, and there are possibilities to have monetary or non-monetary benefits. And this is usually, these contracting partners agree on non-monetary benefit sharing. So this would include capacity building of research infrastructure development in the country of origin, for example, but can also include something like the sharing of data or scientific collaborations, so that certain researchers from the country of origin will get invited to a position at a Western university, for example. And this is, so the Nagoya Protocol is running since 2010, and it is still not finalized even though there are a lot of contracting parties, a lot of countries do not participate in there, and some countries are only just starting to consider under what conditions they allow research to take place on their grounds. But it is something that is already implemented and that is developing and shaping up, also being controversially discussed, particularly in the context of COVID-19, where it's sometimes blamed to sort of restrict the sharing of data, because it forces researchers to enter these, to stick to these agreements, right? So it is controversial, but it is, particularly for countries of the Global South, a mechanism through which they can get some sort of control over the benefits that emerge from research. And more recently, there are similar discussions around this idea of access and benefit sharing in the so-called BBNJ negotiations, which are also taking place in the United Nations since 2018. And what we can, and these negotiations are about biodiversity beyond national jurisdiction. This is why it's called BBNJ. And this relates to the fact that there is a rising scientific and commercial interest in biodiversity from the deep seas. So from essentially biodiversity that exists thousands of meters deep in the ocean, right? Which is often in these waters beyond national jurisdiction. And this is a different issue than what the Nagoya Protocol covers, because you cannot make bilateral agreements with the country of origin in that case, right? Because it's non-state territory. So, and there is a tension in international law between two principles here. So one is the freedom of the high seas, which subscribes to freedoms to actors to, for example, navigate the high seas freely, but it also involves freedoms to do research in these non-state areas. But there is also the so-called common heritage principle, which obliges actors who take resources from non-state areas to share them amongst the global community of states, particularly particularly when they are taking from the ocean seabed. That's how it's specified in international law. And when it comes to these genetic resources, it's unclear whether they fit more to the freedom of the high seas principles or to the common heritage principle, which would mean there's more obligation to share the benefits that would emerge from this research. And similarly to the case of vaccines and so on, you can see there's some very nice research on who owns patents that were warranted using genetic sequences from marine organisms. And here we also see a strong focus on Western companies, particularly on one company, BASF, a German company, which owns 47% of all patents of that kind. So it's a similar picture. The question, science only for the West, applies quite nicely to that case as well. So, and this is why we see in these negotiations, in these BBNJ negotiations, conflict between countries of the global North and countries of the global South over how to exactly design this access and benefit sharing mechanism, right? And this is particularly about how should the benefits look like. Again, this distinction between monetary and non-monetary benefit sharing. And in this case, currently the discussions revolve around how monetary benefits could look like. And one idea is that the patent licensing fees, which would occur when someone owns a patent and another company wants to use this patent to develop something else. And this company would pay these licensing fees to the patent holder in order to legally use the knowledge or the innovation that the innovator company owns, right? And there's this idea that countries of the global south would get a certain share of these licensing fees that would result from such a process. But this is controversially discussed, and countries of the global north really don't want to open up patent law and negotiate over this. But, well, this is an open discussion that we are also observing at my research project. And just to close off our presentation, some take-home messages, or like to summarize what we've been talking about. So in science, we see an increased focus on large-scale data creation, sharing, and analysis. And this happens both in practice and in discourse. So it happens in terms of the scientific methodologies and approaches, which are the practices, but it also happens in discourse. So there's increased focus in policy discussions or in public debates, that this big data has emerged as a sort of central theme in science. And we talked about the various challenges that arise from this process. And we talked about epistemological challenges, which can be captured by this question, as science of only numbers, and questions around equitability, which is this point about science only for the West. And we hope that we think both of these sort of challenges open up critical understanding, and also an understanding of the governance challenges that are linked to the process of big datafication. And one further takeaway point is that science and scientific data is governed by a heterogeneous network of governance institutions and frameworks, some of them being more informal, bottom-up initiatives coming from the scientific communities themselves. But they always have to interact with national science policies, and also, as you saw in the last example, also with international treaties and international law. Finally, we want to point out that big datafication of science is really relevant to talk about because of the many consequences it has for societies. Just think about COVID-19, where you can see all of these issues sort of become very relevant in today's context. That was it from us, from our presentation.